I'm going to be explaining Apollonius, Book 1, Proposition 21, which says, if in a hyperbola or ellipse or in the circumference of a circle, so we have a hyperbola, an ellipse, and a circle, those three shapes, straight lines are dropped ordinate-wise to the diameter, the squares on them will be to the areas contained by the straight lines cut off by them, beginning from the ends of the transverse side of the figure, as the upright side of the figure is to the transverse, and to each other as the areas contained by the straight lines cut off, abscissas, as we have said. So we have these three shapes, hyperbola, ellipse, and circle, and it says, if in any of these shapes, straight lines are dropped ordinate-wise to the diameter, that's going to be these lines here in all of these shapes. The squares on them, the squares on these ordinate lines, will be to the areas of the rectangles that we create on this side of each of the shapes. That's kind of what he's saying. So, he says, let there be a hyperbola or ellipse or circumference of a circle whose diameter is AB. So we have AB here, and AB here. So that's the diameter in all three shapes, and whose parameter is the straight line AC. AC is here, AC is here, AC is here. So that's the parameter, or the upright line, as we are calling it as well. The parameter is the straight line AC, and let the straight lines DE and FG be dropped ordinate-wise to the diameter. So DE, FG, DE, FG, DE, FG, they're all dropped ordinate-wise to the diameter, which is AB. He says, I say that the square FG, so the square here, is to the rectangle AG, GB, as AC is to AB, and the square FG is to the square DE, as the rectangle AG, GB, is to the rectangle AE, EB. So that's what he's trying to prove. He says, for let the straight line BC determining the figure be joined. BC, BC, BC. So that's the determining line that we've been talking about. And through E and G, let the straight lines EH and GK be drawn parallel to the straight line AC. So we've drawn EH and GK parallel to the straight line AC in all of these shapes. So he says, therefore, and we can come over here, the square on FG is equal to the rectangle KGGA, and the square on DE is equal to the rectangle on HEEA. So we can kind of look over here to see that. The square on FG is equal to the rectangle KGGA, and the square on DE is equal to the rectangle HEEA. And that is because of propositions 12 and 13, earlier from Apollonius that we've been talking about, where the square on the ordinate line is equal to the rectangle, which includes the upright side and the abscissa. I can't say it properly. But it's those two lines that create that rectangle, and the square is equal to that. So that's what we're seeing here. This square is equal to this rectangle, and this square is equal to this rectangle because of the propositions about a hyperbola and an ellipse. We don't have a parabola, so we're not using that proposition. And so since this is where it gets tricky and where I kind of added my own interpretation, he says since KG is to GB as CA is to AB, and I've drawn HE and HE is to EB in red because he does not include this in his proposition. It's assumed, and I think is really confusing unless you draw it out, as will kind of be noticed later on. So I wrote that KG is to GB as HE is to EB as CA is to AB. And so we can see that here. KG is to GB as HE is to EB as CA is to AB. We can see that those are all similar. So we have this here, and then this is where he kind of goes into his proof. So he says we're going to take AG as common height. So here's AG here. AG, AG. We can see AG in all of those things. We're going to take AG as common height, which is basically the way that this looks is that we're up here we just have lines. We just have specific lines like KG and GB, and we're now making these lines into rectangles by adding AG as the common height. So KG is to GB, which is exactly what we have up here, as rectangle KG, which is what we have over here, but we're adding AG. As rectangle KG GA is to rectangle BGGA. So essentially we've added AG to both of these lines and made them rectangles. So KG is to GB as rectangle KGGA is to rectangle BGGA. And then he says CA is to AB as rectangle KGGA is to rectangle BGGA. So he's dragged these rectangles down, but he's changed this. And the reason he's changed this is because up here we've proved that these are all proportional. So then he says CA is to AB as square FG is to the rectangle BGGA. We've dragged this down and we've dragged this down, but this is different. And the reason that we can substitute square FG is because of up here. Square FG is equal to the rectangle KGGA. So we've just replaced this rectangle, and we now know that it is these are proportional. Okay, so then this is the part that Apollonius does not write in his book, but I think is assumed, and it was really confusing for me, so then I wrote it out myself. So he moves on to this line that we have right here, but before that, we're going to go to this. So we took AG as common height just barely, and it's implied that you can also take AE as common height. And that's what these look like. So this is all R.E. Johnson math here. This is an Apollonius, but I think it is assumed. So now we're going to take AE is taken as common height, and that means that we now have HE is to the HE is to EB as the rectangle, HEEA is to the rectangle BEEA. So essentially we've done exactly here what we already did up here. And then we're going to do the same thing. CA is to AB as rectangle HEEA is to rectangle BEEA. CA is to AB as rectangle HEEA is to rectangle BEEA. Okay, and so then we come down here, we do another replacement. CA is to AB as square DE is to the rectangle BEEA. How can we put that square in? Because up here we know that the square DE is equal to the rectangle HEEA. So we substitute that with the square. And now, after this math that I have now added, we're back on track with Apollonius. And this is what he says. CA is to AB as square DE, this square here, is to rectangle BEEA. So that's where he ends up. And then he says, therefore, the square on FG, this square here, is to the rectangle BGGA as the square on DE is to the rectangle BEEA. And he says alternately, the square on FG is to the square on DE as the rectangle BGGA is to the rectangle BEEA. So this proposition I think is just really cool because he's basically shown that all of these ordinate lines that we have drawn off of the diameter and these lines that we've added that are parallel to the parameter are all basically proportional. Like through this, we've seen these are all proportional, and then his conclusions, we've seen that they are proportional as well. FG is to this rectangle, DE is to this rectangle, but these squares are also to each other as these rectangles are also to each other. In all of these shapes, the parabola, the hyperbola, the ellipse, and the circle, they are all proportional, these squares to these rectangles. And that is QED.